Welcome to this video. In this video, I will be talking about the 422 code as the smallest code that detects X and Z errors. So it does not correct it. So similar to the 311 code. So I just showed that 311 code, which was the bit flip code. It could not correct the phase flip error. But this code, it could not even detect phase flip error. So this could not detect Z errors. So could not detect Z errors, but this code will detect them, but it will not be able to correct them because it will not show us which position the error occurs. So let's go through the circuit. So first of all, because we have understood kind of the stabilizer formalism, I say that the stabilizers for this code is this and this. So these are what are being applied here as conditioned operators. So it's x1, x2, x3, x4 and z1, z2, z3, z4. Now first thing that one would like to check is that S should be an abelian subgroup of P, the Pauli group. So one would like to check that whether these operators commute with each other or not. So do they commute? But this checking can be quite cumbersome. So there is a nice theorem or a nice kind of way to quickly check the fact whether they commute or not. So I will not prove this, but it's simple to prove based on the commutation relation of single Pauli operators. So two Pauli operators P and P prime, they commute if they intersect on an even number of terms with a different Pauli element. So let's check this here. So I am seeing that they are intersecting on 4 terms, and on the 4 terms they have different Pauli elements. This means they automatically commute. So let's look at some other example, an example where they anti-commute. So let's look at these two Pauli operators. So you can see that they are same on x1 and they are different on exactly one of the places. So out of the 4 qubits, so this operator is x1 identity z4. So I will not include the identity operators. I will not consider those places. So I will ignore the 2 and 3 place, and I will only focus on 1 and 4 place. In the first place they are same, but in the last place they are different. So they are different on one side, that is namely 4th qubit. So this means they anti-commute because this is an odd number. 1 is an odd number. Similarly, let's look at another example. I have x1, x2, x3 and z2, z3, z4. So I will not look at x1. I will only look at 2 and 3. And they are different in 2 sides. So different on 2 sides. So commute. So this is a quick way to check. With this, let's come back to our circuit. So this circuit takes 2 physical states along with 2 another qubits, and then this is the encoder. So this entire thing is the encoder, and then this is the error, and then I have these ancillary qubits which will detect and measure the syndrome. So a quick way to check what is the code space is first to understand that the code space is the space stabilized by this S. So that is by definition. And if you put 0, 0, 0, 1, 1, 0, 1, 1 to psi1 and psi2 respectively, what you will get in the output space is the logical words. So this is what I have written here. So 0, 0, 0, 1, 1, 0, 1, 1, they are of this form, and you can put each of these and verify for yourself. And you can also show that the stabilizers actually keeps these code words invariant. So the entire span is kept invariant by the stabilizer. So with this we will perform the circuit. So it's easy to perform this circuit because we have already seen the bit flip circuit, and that also had exactly 2 syndromes. So the bit flip circuit also had two syndromes, Z1, Z2 and Z2, Z3. Instead of this, I have two syndromes of this form here. So I can easily perform the circuit, and I am directly writing the final result, which looks like this, as you can see on the screen. So again, you can see that there are negative signs and positive signs in a very specific way, such that they will help us to detect the errors. So if the syndrome is 1 0, the claim is I can say that a single bit flip error has occurred in one of the qubits. I don't know which qubit, so information is not there about which qubit. Let's see why this is the case. So if it is 1 0, then you can see that if I have a x error, then it commutes with all the x's here. So this term is not contributing. I mean, this term is contributing +1 because of the commutation relation, and this has a sign of +1 also. But these terms which have -1 sign, they will actually anti-commute and give +1. So the entire probability will be 1 to obtain this state. So I will measure 1 0. Now it is invariant, so it does not depend on whether it is x1, x2, x3, x4, because exactly at one site it will fail to commute. So similarly, you can have 0 1 and 1 1, and you can show that this happens. For example, if I have Z1 error and I have the 0 1 syndrome, then it actually anti-commutes with these two, x and y. Similarly, if I have y, it will anti-commute with x and z. So this is the code that is called the 422 code. So you can see that here there are two logical qubits instead of one. So that is something different. And finally, we come to the Shor code, which is an example of concatenation of two code. One code is the bit flip code and another code is the phase flip code. So let's see the Shor code. Shor code is a 913 code, such that I have 9 qubits inside the encoder. I have one logical bit, and I can correct all the single bit flip errors. So a three flip error will go undetected. So this is the idea. Now let's see how we can concatenate two codes. So we have the code space for the bit flip code. So B is for bit flip. So it is 0 1, such that they are logical. So instead of logical, I am writing B because B is for bit flip. So they are of this form, and the stabilizer is of this form. So the stabilizer completely defines the code space. Similarly, I have phase flip code, and it has this as the logical bits, and I am denoting it by this, and this is the stabilizer. Now what is code concatenation? What we will do is we will embed bit flip code into the phase flip code. So I take my phase flip logical 1 and logical 0, and then I put just bit flip logics instead of normal computational basis. So this is the change that I make. So I make a transformation from the phase flip code to a 0 9 code. So there are now 9 qubits inside the encoder, and I have just concatenated two code. I have put one code inside the other. So now I define my code space in this particular fashion as span of 0 9 and 1 9. So the 9 in the subscript, it will stand for number of physical qubits. So this code has a stabilizer which has 8 elements, 1 2 3 4 5 6 7 8 here. So it has 8 elements, and how we can decide which are the elements? It is simple, because we have used a concatenation technique. So the idea is, inside the phase flip, I have the bit flip, which will talk about flipping between 3 bits at a time. So I have 1 2 3, and Z1 Z2 Z2 Z3 talks about flipping 1 2 3. I have 4 5 6, Z4 Z5 Z5 Z6 talks about flipping those, and I have 7, 8, 9, and Z7, Z8, Z8, Z9 talks about flipping those. Similarly, I can talk about now flipping plus to minus, and that is done on the 4, 5, 6. So I have x1, x2, x3, x4, x5, x6, and similarly x4, x5, x6, x7, x8, x9. So now we remember an important thing to check the syndrome. So the syndrome can be deduced from the fact what we have seen for the bit flip code. So for bit flip code, for which the stabilizers were Z1, Z2 and Z2, Z3, if we remember, we had syndrome 1, 1 associated with the second flip, syndrome 0, 1 associated with the third qubit flip, and syndrome 1, 0 associated with the first flip. Now we will use that to measure the or deduce the syndrome in case of Shor code. So in Shor code, suppose I have a bit flip in the first qubit. Then the syndrome corresponds to taking the first two ancillary bits corresponding to measurement of these two operators. So every operator will have an ancillary bit corresponding to it, right? So there is an ancillary bit corresponding to every stabilizer. So I have in total 8 ancillary bits, and now the syndrome will be 0 and 1s in these ancillary bits basically. So if I have Z1, Z2, Z2, Z3, I will have a first bit flip means a 1, 0 in the first two of the ancillary bits, because the first two are coding for Z1, Z2 and Z2, Z3. So if I have 1, 1, I know that the error is on X2. If I have 0, 1, the error is on X3. Similarly, I have 4, 5, which is coding for third and fourth, and 5, 6. So this I have shown here. Again, you will have the same pattern that 1, 0, 1, 1, 0, 1 will code in a appropriate way. And similarly for X7, X8, X9. So you will have 0, 0, 0, 0, 0, 1, then 1, 1 and 1, 0. So this was the reason why we used these pair of Zs. And now what about the last two stabilizer? So when we measure the last two stabilizer, we get a syndrome in the last two bits, bit 7 and bit 8. And that also corresponds to a bit flip error, but in the plus minus basis. So you can see that this error syndrome is actually degenerate now, because there are just 3 errors, but it needs to correct for 9 different phase flips. So how does this work? So this works because of this concatenation technique. So we have entire block Z1, Z2, Z3 that corresponds to this first plus, and that will have a 1, 0 that corresponds to X1 error. So X1 error in that case. So similarly we have Z4, Z5, Z6, and that corresponds to 1, 1, which is an X2 error. And then Z7, Z8, Z9, which is an X3 error. Where 1, 2, 3 are now the concatenated bits. For example, the bit 2 is actually 4, 5, 6. So maybe I write it 1 prime, 2 prime and 3 prime. But now how the error is corrected is the question, because if I have these 9 syndromes, if I have these syndromes, then I can apply the bit flip again. So apply a bit flip again, because I know the exact position also. But if I have these syndromes on this side, which are phase flip syndromes, they are degenerate in nature. So for this, what we do is we use the idea of the fact that we have the stabilizers at hand. So suppose I have these 3 errors, and I say that whenever I will have 1, 0, I will apply Z2, for example. So now it's easy to see that Z1, Z2 as well as Z3, Z2, which is Z2, Z3, they both are stabilizers. So the recovery happens in this particular way. So if I have a Z1 error, I apply Z2. This is a stabilizer, so it projects or it maps onto psi. So a stabilizer keeps psi invariant because that's the definition of the code space. If I have Z2 and I apply Z2 again, it is Z2 square, that is plus 1. And if I have Z3, I can apply Z2, and this is again a stabilizer, and this gives us psi again. So using the fact that I have the stabilizers at hand, I can still perform the error correction even though my code is degenerate. So that's all for this video. I hope I could convey the important message of Shor code, code concatenation, and also the other code that I discussed. So in the next video, I will talk about quantum error correction conditions, which are also called these particular clean Laflamme conditions. So let's go to the next video.